Let's go. Finishing up for today. Linear algebra. Save the best for last. Now, what did we learn yesterday? Well, we finished up, I believe we finished up Appendix B. And I think we're into Chapter 1 today, potentially. We've talked about de Moivre's formula. We talked about Euler's formula. Euler was just about complex numbers or imaginary numbers being in the exponential, or an exponential, yeah, in the exponential. De Moivre, what was that formula? I think it ended up being something simple, but I can't remember now what it was about. We've been talking about complex numbers, probably polar form. Polar form, okay. E to the I to the theta, that's Euler, part of Euler's. De Moivre's, you're going to talk about, okay, polar form. It's going to have theta in there. The angle, okay. Okay. Hearing strange noises. De Moivre. So we're talking about polar form. When you are, what was it? Geometric interpretation of multiplying and dividing complex numbers. That was the first part. Geometric interpretation of multiplying and dividing complex numbers. Geometric interpretation. So basically, in the complex plane, when you multiply complex numbers, the vectors, the absolute value of z is the length of the vector. So basically, to find the length of the vector of multiplying complex numbers, you're going to take the absolute value of each, multiply those together, that's the new length of the vector, and then you're just going to simply add the arguments together. Okay? So for de Moivre's, this is where de Moivre's then come in. In the unique situation where the length of the vector is 1 on both, well then, the absolute value of z, you can just remove that. That's just assumed 1. So then z is going to be equal to simply the, z to the n, right? We're taking z to the n power. Well, then it would be equal to absolute value of z to the n, but that's just 1 to the n. So you can take that out. Z to the n equals cosine n theta plus I times sine n theta. I think we could have got that right. Yeah. Okay, then we say the polar form. So cosine theta plus sine theta, all that taking the exponential n equals what I just said, the other side. Cosine theta times n plus I times sine theta, or argument, times n. So that complex exponential function, e to the I theta equals, the hell does this equal? Cosine theta times sine theta, okay. Right, when the unique situation where the complex number is just I, that's a vector, the length is 1, so it's only going to just geometrically shift the vector 90 degrees. That's all it's going to do. It's not going to change the length because it's only 1 is the vector length. Dividing vectors, then we're going to define that to divide vectors, you're simply going to take, to divide complex numbers, you're simply going to divide the length of the first vector, so the absolute value of z1 divided by the absolute value of z2, so you're going to divide them. And then to find the angle of the new argument, you're going to subtract the arguments. Yep. Okay. That's it. We're done with the Appendix B. So now we are into chapter 1 now. Systems of linear equations and matrices. Introduction to systems of linear equations. I think we just get started. So chapter 1's got a lot of sections. Let's just go ahead and start. I'm going to read the introduction here for chapter 1, and I'll be back. It's amazing, guys. We are actually finally into linear algebra, and I learned about what is linear algebra about. The first question I ever posed. It's about the study of matrices and related topics. Simple as that. What are matrices? Well, they're these basically tables of rows and columns. They're called arrays, rectangular arrays of rows and columns. So 3 points from this introduction to chapter 1. Information in science, math, and business is often organized into tables that are called matrices. Matrices can be used to solve systems of linear equations, apparently, but maybe not just linear, but systems of equations in general, especially because computers are really good with working with matrices. But matrices are more than just ways to solve systems of equations. They are actually unique mathematical objects with a lot of underlying theory and application. And so that was the introduction to chapter 1, and we are now jumping into section 1.1, Introduction to Systems of Linear Equations. So this is going to be much longer than the intro. We've got linear equations as a section, linear systems in 2 and 3 unknowns, figures, examples, augmented matrices and elementary row operations. Oh, wow. Section 1. Okay, then we have exercises on it. Okay, wow. All right, so I'm just going to start working through this section. I'll be back with some recall in a second. All right, guys, there was a lot in that first opening page on linear equations. So I just learned a lot about systems of linear equations right here. Linear equations themselves, actually. I think that was just linear equations. I always thought of linear equations before this as basically a line, right? Anything that represents a line. But quickly I realized, oh, there's way more than lines. In three space, so in 2D, a line is a linear equation can represent a line. But in 3 space, it's actually a plane. So planes in 3-dimensional space are linear equations. And actually, so a line in 2D has 2 variables, x and y, or whatever they are, 2 variables. In 3-dimensional space, you've got 3 variables. Well, there's actually, you can have infinite number of variables and still be a linear equation. A linear equation can be written in the form of basically a1, x1 plus a2, x2 plus a3, x3, dot, 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 a, n, xn equals b, where all a's cannot be 0. You can have all of them be 0 except for 1, but not all of them can be 0, or else that's not a linear equation. So you need at least one of those a's to be a non-zero value. In the unique situation where b is equal to 0, that's called a homogeneous linear equation. So what defines a linear equation? Well, that it can be written in that form I said, basically ax 1, a1, x1, etc. Equals b. So it can be written in that form. All variables, none of them are equal to, or all variables are to a power of 1. They're not to a power of anything greater than 1. There's no products of variables. There's no roots of variables. There's no exponentials. There's no trig of variables. There can be these things as long as they are part of the b value. I think that's defining it, yeah. That form, then none of that, the power. Yeah, I think that's it. can have infinite variables. So this is why linear equations are actually massive systems of linear equation, that is, are a massive part of linear algebra. I always thought there was lines. They're not lines. They're planes in 3-dimensional space, and then there's 4-dimensional space, 5, 6, 7, up to infinity. As long as they're in that form, they're considered a linear equation. All right, I've got 5 more minutes. I'm going to go read a little bit more, and then we'll be back for more recall, and then we'll end today. So I'll talk to you in a second. Wrapping up for today, guys. What did we just learn? Solutions. Right. System of linear equations is also known as a linear system. It basically has it's a finite set of linear equations. The unknowns are the variables in the equations. Solutions are values for the variables in which make all statements or all equations true. And they can be written in the form of parenthesis S1, comma S2, dot, 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 SN, parenthesis. Cool. Oh, that's it for today. We are actually into linear algebra now. Can you believe that? We're learning about actually like a lot. I just learned a lot today about linear equations. Whew. Yeah, we're into section 1.1. It feels great. I mean, those appendices were, I don't know, 10, 15 pages. So considering we're on page 3 now, we're almost 20 pages into this textbook, and this textbook is only 500 and something pages, so we can like actually do it. Like, as crazy as it sounds to slowly go through a textbook, like we're kind of doing it. So I mean, good stuff. This stuff's kind of complex, but looks like we're understanding it well so far. And yeah, talk to you guys later. See ya.